So here in 15.1, we'll look at an introduction to different types of graphs and charts, ways to represent data. So first, a data set is a collection of all your values. They could be anything, money, temperatures. They don't necessarily even have to, everything in it doesn't always necessarily have to be numbers. And then we have data points, so the individual values. So we'll work with data sets where each data point is a single number, but you could have data points where it's a whole bunch of different numbers. Maybe like we measure somebody's weight, height, blood pressure, and we make each person a data point or something, but we're going to go with single number ones here. And then like normal, we'll use n to represent the size of the data set. So maybe 100, maybe 20, it could be millions. Obviously, we'll keep them reasonable for homework sake. Okay, so here's one. We're going to get some of the raw data. The day after a midterm exam in a stats class, the instructor posts their scores online, and it is n equals 75 data points. So that means that 75 students took this exam. And then each data point is a score between 0 and 25. And he gives no partial credit, so there's no like 1.5. You get 1 point or 2 points. And notice the numbers are in the first column are data points. They're numerical, but they're not, they're student IDs, so that he's not just posting what everybody got on the actual exam. So look at these. Oops. So these are just student ID numbers, so that they're kind of anonymous. And then here's all the scores. So these could be names, they just happen to be numbers. And so what we want to do is, looking at this, we can maybe get some sort of idea how the test went, but it's probably not the greatest picture because we're looking at kind of all the raw data. So let's say you go to 16, you want to know, is a 16 good? Well, you scroll through there, you don't see a lot of scores that are higher than 16, so you might feel like that's pretty good. Or let's say you got an 11. Well, I see a lot of other 11s. Is that a good score, or is it kind of in the middle, or is it below average? And so what would be helpful is if we could either make a graph, or what these usually start out with is a frequency table where we count how often each score shows up. So we won't make the whole thing because it'll get a little tedious, but let's say, let's see, I see a 1 here. So let's go with that. I don't see, hopefully, any other 1s in this whole data set. So the score 1 is in the data set once. What's the next lowest score? Maybe like an 8? I see an 8 somewhere. Okay, so let's go with an 8. How many people got an 8 on this test? So there's 1. 2, 3, 4, 5, 6. Looks like people got an 8. So this is all a frequency chart is telling how many times that score shows up on the list. While we were doing that, I noticed some 7s in there too, right? So maybe if we're trying to go in some kind of order, we could say, well, how many people got a 7? Looks like no one in this column. No one in this column. There's 1, 2 people got a 7. So a frequency chart would just go on like that, say, count up how many people got a 12 or an 11. Those ones look like more common scores. You don't have to, but I think it's helpful to cross them off. That way you know if you missed counting any. Okay, so they went and made the frequency table for us, so let's go look and see how the test went. So one student got a 1, one student got a 6, I didn't even see that one in there, 2 students got a 7, 6 students got an 8, 10 students got a 9, 16 students got a 10, 13 students got an 11 on the exam, so on and so forth. So this gives you probably a better idea. 11 is almost the score that people got the most. 10 was the one that's the most, so it's 1 more than that, so at least you're on the larger side. So this makes it a little easier to tell how the test went. Another thing we could do, kind of pictures worth 1,000 words here, is if we graph this data. So there's our 1 person got a 1, 1 person got a 6, 2 people got a 7, 6 people have an 8, 10 people have a 9, 16 students got a 10. So this gets an even better picture of how the test went. We have one really low score, one really high score. A lot of people kind of grouped together here in the middle, with 10 being the score that people got most often, the mode of the data set. Another thing we could do is, let's say he wanted to compare this to a different semester. So this semester there were 75 students in the class, but a different semester, let's say there were more or less students. It'd be a little hard to compare when your sample sizes aren't the same. So another thing you could do is make what's called a relative frequency chart. So instead of putting the numbers, put them as percentages. So first thing you'd have to do is add up, okay, there's 75 students, so 16 out of 75 or 2 out of 75, what percent is that? So 16 out of 75 is about 21-ish percent. Now one thing I want to notice here, we'll flip back really fast, is see how the shape of the data? The shape of it looks exactly the same. The shape shouldn't change. If I change these to percentages, if this one was larger, it should be larger still in the same proportion as this one. You're just changing them to what percent. So 21%-ish of the students got a 10. And between 16 and 18, so about 17% of the students got an 11. Maybe about 1% or a little more than 1%, 1 out of 75. So little more than 1% of the students got a 1. Little more than 1% of the students got a 24. So it's the same data. You could just graph it as a percent of the total. And so one reason that'd be useful is if this semester there were 75 students and another semester there weren't 75, you could still compare the percentages instead of the actual numbers of students who got certain scores on the test. So same thing, you just go through and say, and then let's say if they gave you this, if you know the total, you could get the actual numbers back. If you see one that says, hey, 12% of 75 students, well, that means 9 students. So you can switch back and forth between one or the other. They're the same thing. And then pictograms, similar to a bar graph, they just can use icons or essentially pictures to show your data. So let's say in this one you had to get an 11 to pass. And so he just put smiley faces with them. If you got an 11, a 12, or higher, you passed. If you got a 14 and higher, you did really well, so they put a smiley. If you got a 10 and below, they put a sad face since you didn't pass, but it's still showing the same data. All right, then when you're doing graphs, one big thing to be careful about that people don't notice, I've seen this on the news, I've seen this in a lot of places once you notice it, of people making graphs incorrectly. All right, so let's say they show you the sales at XYZ company. So you're at a meeting, you put this up on the slide. It looks great, your sales are growing for sure, but it also looks like they're growing, I don't know, they're growing really fast. Like here, you were kind of halfway in between here, and now you're 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, maybe 10 or 11 times as much as when you started out here. So that seems like huge growth. Is that accurate? Well, if we step back and look at the scale, notice how this doesn't start at 0. So this is a tenet to try not make a graph misleading. You need to start your scale at 0. So let's say we look at the same data and we start the scale at 0. Does it make a difference in the picture? So it started out at 55 million and went to 80. Or just below 55 million and went to almost 80. See how it still starts around 55 and goes up to 80? But now that the scale goes to 0, you can tell that in relative to the size, now certainly they're still growing, but it's not 11 times as big. So that's the reason it can look really misleading if you don't start your y-axis at 0. So they're just pointing out the same thing. You have to start the vertical axis at 0. Otherwise, you can't, you don't get a picture of the scale. It grew, but how much did it grow by? And then variables can be non-numerical, so categorical or quantitative variables, and qualitative is numbers. So this one, they're showing agriculture, business, education, so they're categories. And then they say how often each of those categories shows up, or in a pie chart, here's different categories, what percent of the total are they? So categorical data, It doesn't have to be numerical. They're telling you how often a certain category shows up. And then on the test score one, they said the instructor didn't give partial credit. So you could get a 10 or an 11, but you couldn't get a 10.1 or a 10.5. So I want to point out, what if there's scenarios where our numbers are continuous, so they don't just jump. So this one, let's say this could be money or something. So if I could get any number in between, instead of just saying, well, this is people are right at 200 and this is people are right at 201, we could make intervals. So this is everyone who fell between 200 and 249. This is between 250 and 299. And so you can pick your class intervals in different ways, but you want to do something to describe where you're starting and ending them. Another thing you can do is, what if these go, so this one's salaries. Someone could make 40,001 cents. They would be in here. So they put the little plus to show that they're at that number, or this is slightly more than that number. So let's say if someone makes 45,000 exactly, they could be in here. If they're 45,001 cents, they would be counted in here. So just deciding where you're going to make your cutoffs when you have data that don't have space between them. So like, once again, on the test scores, you could get a 10, 11, or a 12. You couldn't be in between. But on the salaries, you could be anywhere in between.